Hello, and this is a presentation of our work predicting cybersickness trend and extent based on FMS labeled dataset. And I am one of the authors, Jounghyun. We have focused on creating a dataset with high temporal density, especially the cybersickness data. I would first like to mention why we need cybersickness prediction. Cybersickness is one of the things that hinders virtual reality from becoming a daily life commodity. It limits how long we can use virtual reality, and it happens to almost everyone, where there are researchers and surveys related to it. Overall, cybersickness is something that we would like to minimize, and to minimize it, we first need to understand it more thoroughly. To do so, there were researchers that collects physiological data or other to figure out in what conditions it happens, and our work is also a step in that direction. So the current sit-rep on the matter is that from the works that I have found, the collection interval on the sickness data is usually too sparse. There are some exceptions, but those are answered in binary, whether you are feeling sick or not. There's also an argument to be made on what is collected to predict cybersickness. Commercial devices do not have EEG sensors to read your brain waves 99 out of 100. And while eye trackings are becoming more common and heart rates could be measured with smartwatches, it is not what's included in the base headset. Therefore, predicting cybersickness based on those parameters might not be practical. The last part is that not many are made public. Most of them are shared only within the research group that created it, and it is quite understandable considering the effort that had to be put into it. To improve on what we have mentioned before, we have made our dataset public, and the sickness data was recorded every 0.5 seconds. The participant didn't have to make an input every 0.5 seconds. Rather, if the sickness value didn't change, the previous input was kept in place to be recorded. And this is our test environment, where the user would go through a space ride. We tried to cover all 6 degrees of motion within this environment. When the users change the FMS value by turning the surface dial, the current FMS value and a face icon indicating the severity of the sickness would appear on screen. It fades away within a short time so that it can minimize the impact on the actual recording. These are what we have collected for our dataset. In retrospect, I believe we could have collected more, but sadly it is what it is. The overall trajectory of the space ride is on the right side graph. For our prediction, we used models that could be used for time series data. In our case, we used CNN, LSTM, and multi-head attention and compared its effectiveness. The parameters of the models themselves can be tweaked or changed, so it might yield different results, and there's probably a huge room for improvement, so feel free to try our dataset. The best performing model from our test was the multi-head attention model, where it had the least root mean square error, mean absolute error, best R-squared value, and the least symmetric mean absolute percentage error. So from this point on, if I do not mention what type of model was used, it's the multi-head attention one. This is the visualization of what we have used for the multi-head attention model. And you can pause the video for a moment if you want a more thorough view. In the motivation section, I mentioned that other datasets usually have a bit of term between the cybersickness data collection. We simulated this by unifying the cybersickness data in 60 seconds intervals. And the result shows that by using the resolution ground truth data and creating a model, it might look as if they give an okay result, since the r-squared value or other error values seems okay. But the model created this way cannot predict the intricate ups and downs of cybersickness that happens in real time, as seen on the result when it is used on the actual ground truth data. The graph above is an example of that, where the 60 seconds flattened data makes the model to predict in a staircase-like way, unlike the model trained with the whole data. We also tried removing some parameters from the data to see what impacts it the most. While removing just the linear acceleration or the angular velocity, it did not matter much. However, removing the personal data did affect the result, decreasing the accuracy a bit. And counterintuitively, removing the timestamp slightly increased the accuracy. We also note that while removing the personal info did not affect the usual error measurements that much, when the personal info is removed, the models seem to fail to capture the trend of the change, as shown with the dynamic time warp values. The table above are examples from some participants. In conclusion, we created a public dataset which also has a high temporal density, and we made each test subject to rest a day before coming to the next one, to reduce the carryover effect. While the accuracy isn't as great as the models in previous researches, we managed to reach reasonable performance without the physiological data. In retrospect, I think that the model might have shown way better accuracy if we recorded the info from the headset, like the tilt of the head and etc. Because if sensory conflict is the main cause of cybersickness, by capturing the virtual movement and the actual movement of the head, it might have worked better. We also recorded all our data in a single test environment, and the recording was made while the subject was sitting, so it might not be applicable to dynamic situations. If it is a dynamic environment, I believe that recording the inputs from the headset gyro and etc. would help, and would like to try this if I get a chance to expand on this work. Thank you for listening, and this is the end of our presentation.